So our lecture basically starts with the problem of diagonalization of a matrix. So and then we will look into these concepts which are in the title of this lecture, which is minimal polynomial and geometric multiplicity, and when do they actually help us in the process of quote unquote diagonalization. So in the last lecture we saw that we had a matrix. So I am picking up the same matrix from the last example. So we had a matrix like this, and this was having a, you can easily see which are the eigenvalues. These are 1, 2 and -1, so you know which will be the diagonal matrix. So this matrix is diagonalizable. It has distinct eigenvalues 1, 2 and -1. So the diagonal matrix will be like this, which will have all the eigenvalues in the diagonals, and for each eigenvalue we had found out eigenvectors which actually form the columns of the modal matrix. So this is a modal matrix, and the eigenvectors are 1, -1, 1, 1, then 0, 3, 1, and then 0, 0, 1. These are the eigenvectors. So you can easily understand one thing here, that since we had distinct eigenvalues, we had distinct eigenvectors also. Suppose the case was this, that my A matrix, I will not write the diagonal matrix here anymore, you can understand very well. Okay, let me write the diagonal matrix here. So it would be 1, 0, 0, 0, 2, 0, 0, 0, minus. So it is like, you can read it in this way. So you had a matrix A to start with, whose eigenvalues you know, and the eigenvalues are distinct in nature, and we figured out the eigenvectors for those eigenvalues which are also distinct to each other. Since the eigenvalues are distinct, the eigenvectors are also distinct, and those eigenvectors form the columns of the modal matrix. And if you do a M inverse AM, then you would get this diagonal matrix. This is nothing but M inverse AM. So you get the diagonal matrix. So the diagonalization process is quite easy and straightforward, and you can completely diagonalize the matrix A. However, suppose you have the matrix like this, another matrix A, which is this 1, -1. Suppose I have 1 here and I have this. So now you see that two eigenvalues are same. This 1 and this 1 and this -1 are the eigenvalues of this matrix A, and these eigenvalues, these two eigenvalues are same and both are equal to 1. You can very well understand that if you calculate the eigenvectors now, since the matrix has changed, I don't know exactly what would be the eigenvectors right away, but you can very well understand that the process of calculating the eigenvectors, which was to form the matrix A minus lambda I, and then take the columns, do the column operation on these, and figure out that which set what is that what is that vector which is giving you a zero vector at the top. So you will look at the bottom and you will figure out the eigenvector. So so that is the case. So while figuring out the eigenvector, it basically means to find out the basis of the null space of this matrix. So since your uh, lambda is 1 and you are using this one again and again to find out, so to find out two basis vectors, you can have a very good guess that you are trying to find out the null space of A minus I, and the basis vector that you will find out would be exactly the same when you are trying to find out the null space of A minus I one more time. So you will land up with two basis vectors which are same. So you will land up with v1, again a v1, and then a v minus 1. So 1 means the eigenvalue here, suppose. So v1 is the eigenvector for eigenvalue 1, and then again the same eigenvector, and then another eigenvector of for the eigenvalue minus 1. So this is generally the case, and then what will happen, that your modal matrix will not be a non-singular matrix anymore, because for non-singular matrix we need all the column vectors to be independent, but here you see that two column vectors will become the same, and that means you will not be able to do this operation. So this operation becomes invalid since M inverse does not exist, and so you will not get a lambda. A diagonal matrix will not be able to be formed because the modal matrix, you were not able to construct a modal matrix. So is there any way out? Is there any way out? So yeah, there is a way out, and you might know that when we are not able to diagonalize a matrix, then we can always do something, which is take the matrix to Jordan form. The Jordan form is quite similar to the diagonal form. Some of you may already know this, but if you are not knowing, then it is also fine. Let me just change the eigenvalues here a bit, because it might be confusing when I am drawing the Jordan form. So I will make this 2. So the theoretical discussion so far remains the same, whatever be the eigenvalues. Just make this 2 maybe. Yeah. So now you have these eigenvalues, two equal eigenvalues, and another eigenvalue which is distinct to this. So for these, the problem happens because of these equal eigenvalues. You are having the same eigenvectors, and hence the modal matrix that you will be able to form will not be invertible, and you will not get a diagonal form. So what to do in this case? In this case, there is a form which exists which will not be the diagonal form, but it is very close to the diagonal form, and this is like this. And here you see this is called the Jordan form, and this particular block that you can find has a very distinct nature, and like the eigenvalues, which are the similar eigenvalues, the same eigenvalues, or we also use the word repeated, that is the more common word. The repeated eigenvalues are lying in the Jordan block, and the Jordan block looks like this, that you have a upper diagonal So here there is only two blocks, that's why you can't see a diagonal but only one element here. The upper diagonal has ones in it and the diagonal has the eigenvalues in it. So suppose I change my A matrix a bit. Suppose I choose another A, 2, 1, minus 1, 0, 2, 1 and 0, 0, 2. So all three eigenvalues are distinct. Then your J would probably be this 2, 1, 0, 0, 2, 1, 0, 0, 2. So now I think you can get a better understanding of how the Jordan block looks like. It is all the repeated eigenvalues on the diagonal and ones on the upper diagonal. Ones on the upper diagonal. So that is the thing. So if you had if you increase the order, so if you had 4 repeated eigenvalues, then this would also increase another order and a 1 would come here and a 2 would come here. So in this way you can increase the size of the Jordan block and figure out what the Jordan form would look like. Now, while talking about talking about introducing the Jordan block, so I wanted to introduce the Jordan block first and then pose some questions whose answers I will give, and then a more accurate understanding of the Jordan block or making the Jordan form will come to you. So saying that, I have made some inaccurate or some things I have said which is not completely correct. So what are those things? So those things actually will lead us to several questions. So what are those things which I have said and that is not completely correct? The thing that I said about the eigenvectors being always equal for equal eigenvalues is not always correct. That means you can have repeated eigenvalues, but you may have distinct eigenvectors. This is possible. You have how when it is possible? So you'll ask me the question, sir, why I am not able to see this? So I will do a minus 2I and I will find the null space and I will get a vector, and if I do a minus 2I again and find the null space, I will again get the same vector. Of course you will get the same vector or you will get the same vectors, because there is every possibility that the null space of a minus 2I has a dimension of 2. Here when I was discussing this, I had very implicitly or very tactfully I considered that the null space of a minus 2I has a dimension of 1. So if it has a dimension of 1, you will get only one vector, and no matter how many times you repeat the same operation, you will get the same vector again and again. But if the null space of a minus 2I has a dimension of 2, then of course by doing the column operation you will get two basis vectors of the null space, and those two basis vectors will be two different eigenvectors. Basis vectors means independent vectors, so these will be two different eigenvectors that time. So one thing that is important to check is the dimension of the null space of the repeated eigenvalue with the repeated eigenvalue, null space of A with the repeated eigenvalue. That means if lambda is having repetition, you try to see what is the dimension of A minus lambda I. Okay, that thing will matter, that this thing will matter. Okay, and this has a very unique name. This is actually this dimension of the null space of A minus lambda I is called the geometric multiplicity of lambda. This is called the geometric multiplicity of lambda. Sometimes we write it as mg lambda. What is the algebraic multiplicity of lambda? Algebraic multiplicity of lambda is the repetition of the eigenvalues in the matrix A. So as many times it is repeated, that is the algebraic multiplicity. In this particular case, for this case, MA2 is 2, MA1 is 1. I assumed that MG2 is 1, which is most of the case you will find this is happening, but not always. Okay, and this is minus 1. Mg minus 1 is also 1. If there is distinct eigenvalue, there is no possibility that the dimension of the A minus lambda I will be more than 1. This you have already had the experience of calculating the eigenvectors. You have seen that for a distinct eigenvalue, I am getting a distinct eigenvector. The dimension of the null space is only 1. So the dimension of the null space cannot actually exceed the algebraic multiplicity of the eigenvalue. So the geometric multiplicity will always be less than or equals to the geometric multiplicity will always be less than or equals to the algebraic multiplicity. So we have to actually figure out what is the geometric multiplicity. This thing that I was talking about, so when I am talking about that A being of this particular A is giving me a Jordan form like this, I implicitly considered that mg of 2 is 1. I implicitly considered this. So if the dimension of A of the null space of A minus 2i is 1, it is only giving me one eigenvector, and with that one eigenvector the Jordan form that will come out will have this form. So all the three algebraic multiplicity, so now the algebraic multiplicity is 3 and the geometric multiplicity is 1. So you will have a block, we will have a single block of Jordan, or a single Jordan block you will have, and we know the structure of the Jordan block. The Jordan block is always like this, that the eigenvalues will form the diagonal and they are the same eigenvalues, and ones will come in the upper diagonal. So this is the form of the Jordan block. How many Jordan blocks will be there is actually decided by the geometric multiplicity. How many Jordan blocks are there is decided by the geometric multiplicity. So once you would know that the geometric multiplicity is 1, I have not calculated, okay, I really don't know exactly what is the geometric multiplicity. I am assuming that it is 1. When I do the calculation like this and do the column operation, I will exactly come to know. We will do one thing once we will do that, but just before that, just to introduce the Jordan form, I am assuming that the geometric multiplicity is 1. If the geometric multiplicity is 1, that means there will only be one Jordan block in the Jordan form. So this whole thing is the Jordan form. This whole thing is the Jordan form. How many Jordan blocks are there? How many Jordan blocks are there? We are only looking for Jordan block for the repeated eigenvalue. So since I have seen that I have assumed here actually again that the geometric multiplicity of the repeated eigenvalue is 1, so there is only one Jordan block for the eigenvalue 2. So I have written it like this, and I would also know the size, the total size of the how many eigenvalues would I have to place here. That is the algebraic multiplicity, right? The algebraic multiplicity 2. So the size of the Jordan block is 2. Here only one the geometric multiplicity is only 1, but the algebraic multiplicity is 3. So I have to place one Jordan block and 3 eigenvalues. So the Jordan block will look like this, and it completely forms the Jordan form because there are no other eigenvalues to be placed. Here in this case there was another eigenvalue to be placed. So I hope you have got this one. Now let me pose a problem like this, that if I have mg2 equals to 2, suppose I find while doing this operation that mg2 comes out to be 2, then what would be the Jordan form? So in this case I will show it with blue, and I will show it in the same block. So if my mg2 is 2, suppose my mg2 is 2, that means there would be two Jordan blocks. There will be two Jordan blocks. Now there are three eigenvalues and two Jordan blocks. That means one of sorry, this should stay here. This will become 0, and one Jordan block will be this much, and another Jordan block will be only this. So this is a Jordan block of size 1, which is the eigenvalue itself, nothing else. This is the Jordan block of size 2. So there will be how many Jordan blocks given by the geometric multiplicity? How many Jordan blocks equals to the geometric multiplicity? 2 Jordan blocks. So you have to divide the 3 eigenvalues between 2 Jordan blocks. So one Jordan block will obviously be of size 1, another will be of size 2. You can very well understand that. One Jordan block have to have a size 1, another Jordan block have to have a size 2. So we can divide it in this manner. So the largest size we can place and on the top, this one we can place in the bottom. We can also change it. We can also place the single Jordan block here and the double Jordan block at the bottom. That also can be done. So this would be the Jordan form. So in this Jordan form, this 1 will become 0. Okay. So that is what will happen when you have your geometric multiplicity not equals to 1. Then the thing will become a bit more complicated. Okay. So it will not be a straightforward Jordan form. The total thing will not be a single Jordan block. There will be multiple Jordan blocks. How many Jordan blocks? As much as there are the geometric multiplicity. So if for this simple example you are able to understand that one Jordan block will be of size 1, another Jordan block will be of size 2. But consider a general example or a general matrix where there are so many repeated eigenvalues. Many repeated eigenvalues are there, and suppose you get your you have your ma lambda as some value, maybe m, and your mg lambda as n, and this can be any values. So then what will happen? You will of course understand how many Jordan blocks you have to construct, but you may not have any idea of what would be the sizes of the Jordan blocks. How to place the Jordan blocks in the Jordan form, you may not have any idea. So to get an idea of the size of the Jordan blocks, we have to come to another concept, which is the concept of minimal polynomial. I will describe the concept of minimal polynomial uh, in this lecture, and uh, not talk about how it relates to the size of the Jordan block. That will be taken up in the next lecture. But before going into the concept of minimal polynomial, let us just investigate for once what was actually the geometric multiplicity of these eigenvalues 2 in this matrix and this matrix. Let us take only one matrix. You can do for another one. Let us take this matrix and see what was actually the geometric multiplicity. So let us do that exercise, and okay, so I will do it here. So let me just clear this. So a minus 2i first you have to construct, and that is very easy to do. This is simply this one, 0 0 1 0 0 0. Already you have a 0. Already you have a 0 column, and you can very well understand looking at the other columns that there is no possibility that you can actually get another 0 column. So it is very obvious now from this matrix, looking at this matrix, that your mg2 is basically 1. And what is that vector which spans the null space? What would be that vector? You can see from here, your x actually, this vector, the null space, if you write a vector v here, the x1 would get multiplied with this, x2 will get multiplied with this, x3 will get multiplied with this. So x3 basically can be anything, because it is resulting in a 0 contribution. So let us take x3 as 1. What would be your x1? You see x1 is coming here as well as minus here. So x1 has to be 0, because if it is not 0, then there is some x1 coming in the second coordinate, and that will come in the result also. So x1 has to be 0. Once x1 becomes 0, x2 also becomes 0, because otherwise there would be a contribution here of x2. So this would be your eigenvector for the eigenvalue 2. You can very easily deduce it from looking at this matrix itself. Now let us talk about minimal polynomial. This is a very important concept, and when I am discussing it, I will discuss from the mathematical point of view, and you might not get a very direct relevance to the eigenvector problem, but that will be taken up in the next lecture. So let us look into the minimal polynomial from its how it is being described in mathematical parlance. So what is the minimal polynomial? So you have a characteristic polynomial. So if you have a matrix A So characteristic polynomials are defined for matrices A. How you will try to see this equation, and this equation will actually be a polynomial in lambda, and that we can, for the purpose of being general, I will write it as x for the time being. So this will be a polynomial in x, and that is called as the characteristic polynomial. So this is referred to as the characteristic polynomial of A. That polynomial which is actually the only the determinant, not don't have to make it equal to 0. The determinant of xi minus a, when you it will be a polynomial, and that is the characteristic polynomial of A. What we know that from Cayley-Hamilton's theorem. So there is a theorem called Cayley-Hamilton's theorem, which is very important. Cayley-Hamilton theorem says, basically it says that the matrix A satisfies its characteristic polynomial. Satisfying the polynomial means basically when you put that value. So if you put a instead of x is any variable, right? So you can place a matrix now instead of the scalar variable, then it satisfies means it becomes 0. So the matrix A satisfies its own characteristic polynomial. That is what it is, and it is very easy to see from here. If you just put A here, this will basically be 0. So the Cayley-Hamiltonian theorem states this, and it is actually not a statement but an implication of Cayley-Hamiltonian's theorem. Cayley-Hamilton's theorem is actually much broader. It actually says something else. It actually says that for any function of the eigenvalue of the matrix A, so if any function of the eigenvalue of matrix A is equals to 0, then the same function with the matrix A itself will also become 0. This is what actually Cayley-Hamilton's theorem says. This is Cayley-Hamilton's theorem, and this is one implication of that Cayley-Hamilton's theorem, because you know that the characteristic polynomial is satisfied by the eigenvalues of the matrix A. So if a function is satisfied by the eigenvalues of the matrix A, then the matrix A will also satisfy that function. This is Cayley-Hamilton's theorem, and one implication of it is that it also satisfies its own characteristic polynomial. However, it does not. So if I ask you the question, yeah, I'm pretty sure that it is satisfying the characteristic polynomial, but is it the minimal polynomial or the minimum order of the polynomial that the matrix A can satisfy? Now I am coming to orders of polynomial. You know that the characteristic polynomial is nothing but x minus lambda 1, x minus lambda 2, so on, x minus lambda n equals to 0, and each of these can have some powers also, right? Some power, say k1, k2, 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , So why I can actually write that PAX is equals to, it is putting this 0 all the time. The polynomial is this. So polynomial is without the 0. So now this polynomial can be basically written as this. Supposing there are m number of distinct eigenvalues. So there are m number of distinct eigenvalues, but each eigenvalue can be repeated ki number of times. This ki can be anything. It can be 1 for a certain I, it can be 2 also for another I. So for suppose for lambda 1 it is ki, k1 is 1. Suppose for lambda 2 k1 is 3. This sort of thing can happen. Okay, this sort of thing can happen. So now the question that I am asking is whether this characteristic polynomial is the minimum order of the polynomial which the matrix A can satisfy. When I say minimum order of the polynomial, I am actually trying to look at these indexes k1 to k1 etc, k1 k2 kn etc, and trying to pose the question that suppose k1 is greater than 1, suppose these ki's are greater than 1, okay, then can I take something like, suppose I have x minus lambda 1 to the power of 2, x minus lambda 2 to the power of 2, all of these to the power of 2, raised to the power of 2. Then I am asking the question, can I take x minus lambda 1 to the power of 1, others remaining same, and then also the matrix A will satisfy this equation? If it satisfies, then I will again ask that can I make the power of x minus lambda 2 also equal to 1, and the matrix A will again satisfy this characteristic, this polynomial. So in this way I am trying to see what is the least order of the polynomial which the matrix A will satisfy. What is the least order of the polynomial which the matrix A will satisfy? That is called the minimal polynomial. That least order of the polynomial which the matrix A will satisfy is called the minimal polynomial. You can very well understand that the minimal polynomial, if I write it as max, m capital AX as the minimal polynomial, it will be of this form. What has changed? This index has changed. What has not changed? The eigenvalues have not changed. All the factors must be present. All the factors must be present in the minimal polynomial. But their index can be less than or equal to the index ki, and MAA would be equal to 0. That is the minimal polynomial. So the minimal polynomial max would divide, actually the characteristic polynomial would divide the characteristic polynomial PAX without leaving any remainder actually. So it perfectly divides. That means that each irreducible factor of PAX is also a factor of MAX. That means each irreducible factor means this is one irreducible factor, this is another irreducible factor. So each irreducible factor of PAX is also a factor of MAX. That means all these factors must be present in MAX, but they can be present with an index which is lesser than that in the characteristic polynomial. That is what can happen. So how to so with this idea of characteristic polynomial, the question now comes how to obtain the characteristic polynomial. So if I am given a matrix capital A, the previous question that we are all familiar with, which was to obtain the characteristic polynomial, but now the question is to obtain the minimal polynomial. One thing you can understand very well, if all these ki's are 1, so if all ki equals to 1, then minimal polynomial is same as the characteristic polynomial, because all the factors are only present once and they have to be present in the minimal polynomial also. So that minimal polynomial will be same as the characteristic polynomial. The minimal polynomial will not be equal, in general will not be equal only when ki is not equal to 1. Then there is a possibility. So I cannot say an if then relationship. Now there is a possibility. Ki not equal to 1 makes this possible. Whether minimal polynomial is really unequal to the characteristic polynomial, one has to look into it. One has to actually evaluate it. Let's jump into an example and see what is happening. Let's take this example A 0 1 0 minus 2 3 0 minus 2 1 2. So what is the characteristic polynomial? It is the determinant of xi minus a, which is the determinant of x to 2 minus 1 x minus 3 minus 1 0 0 x minus 2. That would be equal to, so if you do the determinant, if you try to form the determinant, you can start from this quantity actually, and you see it is giving you this thing x square is 3x plus 2, and hence this can again be factorized. What you will get is x minus 2 square x minus 1. That is what you will get. So now you can see that in this characteristic polynomial, one of the factors is having a power of 2. One of the factors is having a power of 2. So there is a possibility that there is a minimal polynomial which is other than the characteristic polynomial, but it can also be same as the characteristic polynomial. So what are the possibilities of the minimal polynomial? So you write them down first. One possibility is this, the same, and another possibility is, so maybe ma1x and ma2x is x minus 2 x minus 1. This is another possibility. Now you have to actually evaluate that whether ma2a equal to 0 or not. You are pretty sure that ma1a would be 0 because it is the characteristic polynomial, but this can also be 0. If this is 0, then the minimal polynomial would be this. and if this is not 0, then the minimal polynomial would be this. So you start from the least polynomial that you can actually form out of the characteristic polynomial. So you have to find out the characteristic polynomial, you have to form the possible lower order polynomials, all possible lower order polynomials, and you have to check from the least order and go up one order and after another. So whichever lowest order satisfies this equation, that would be your minimal polynomial. So here let us see. For this one, so I have to actually have two matrices with me, A minus 2i and A minus I. So A minus 2i is minus 2 minus 2 minus 2 1 1 1 0 0 0. A minus I is minus 1 minus 2 minus 2 1 2 1 0 0 1. Now if you do this, A minus 2i, A minus I, then you will find that actually this would become 0. Let me just walk you through this. So here you can see that this would become 0, then the next one minus 2, this is also 0, this one is also 0, this one is 0, this one is 0, this one is also 0, and this is all zeros because the last row is 0. You get 0. That means your characteristic polynomial is basically, you can now conclude that the characteristic polynomial is this. Sorry, the minimal polynomial. The minimal polynomial is this. You can conclude. So if you have found out the minimal polynomial, there are several applications actually. These applications does not directly link with the eigenvector eigenvalue problem, but this is very important application for evaluating functions of matrices. That is what I will show you. So now you see that the minimal polynomial, since you have already identified, that is equals to also x square minus 3x plus 2, and since MAA equals to 0, what you get from here is this relationship holding true always. This means a square equals to 3a minus 2i. So if you have the knowledge, which is the minimal polynomial, then you can have a relationship between higher orders of a and lower orders of a, like this. This can be very useful. A very practical use you can see, if your A was actually very complicated matrix, then to get a square you can simply do a 3a minus 2i and you would have found out a square. You don't actually have to do the a square by multiplying a with a. Suppose I pose you a problem like this. Let's solve this function a cube plus a square plus I. I want to evaluate a cube plus a square plus I, given the knowledge that the minimal polynomial is x minus 2 x minus 1. That means the A matrix I had given. So I could give you the A matrix. So from there you already would come to know the minimal polynomial, and then you can evaluate this expression as well as other complicated expressions. This is perhaps you can actually evaluate without looking into the minimal polynomial. But suppose you have a power of 6 or even more, even 100. So in those cases the idea of minimal polynomial is really helpful. I will solve this and you will get an idea how to go ahead if you are given a problem like this. The same approach you have to take. Here what I will do, I will try to replace a square. Since I know what is a square, I will try to replace a square here. So a into a square I am replacing by 3a minus 2i. Here also I am replacing by 3a minus 2i, and another I is here. So now I am doing a simple algebra first. So here 3a square. So 3a square again I am writing instead of a square 3a minus 2i. Then I am getting minus 2a plus 3a minus 2i plus I. So you see that 9a, so here it is only 1a, so it is 10a. How many i's? Minus 6, minus 1, minus 7i. You can do this. This is very easy to do. You don't have to go to a cube, etc. So this is simply 10 times the a, and the a matrix, I know what was my a matrix. So accordingly I will write it down. So I am writing it down from my notes, so you can verify what was the a matrix, and multiplying it with 10 times will give you this. So this is the resultant matrix. So you can understand very well that you will come to lower orders of the system. So if you are asked to evaluate a to the power 100, I hope you will be able to do it. It might take some more number of steps for doing the simplification exercise, but ultimately you will find that it is in terms of a and I only. Okay, so that is about the minimal polynomial and how it is used. The one use of minimal polynomial is to find out evaluate higher order polynomials of the matrix A. That is one use of minimal polynomial. In the next lecture we will find the concept of minimal polynomial, how it applies to our problem of eigenvalues and eigenvectors in the situation where I am having repeated eigenvalues and geometric multiplicity of eigenvalue is greater than 1. So then the idea of this minimal polynomial will also play an important part in determining basically the size of the Jordan blocks. Okay, so with this actually I end the discussion. I will give you one matrix and you can try to figure out the characteristic polynomial, the minimal polynomial, and the eigenvectors of this what should I say, not the eigenvectors, the geometric multiplicity of the eigenvalue. So this is the matrix that you can actually work out. This is a large matrix, but don't get intimidated by its size. It's basically very easy to solve. So this is the matrix which you can work with. So what are you required to find out? You are required to find out the characteristic polynomial. You are required to find out the you are required to find out the algebraic multiplicity of the eigenvalues and the geometric multiplicity of the eigenvalues and the minimal polynomial. So these four things you can try to work out for this matrix. So I will leave you with that, with this exercise, so you can have some practice and on the concepts that have been covered. Thank you for your attention. See you in the next lecture.